We now look at some examples on this chapter on collisions, which involve 1D and 2D collisions. So the first one is what's written as an executive stress reliever. And that is the sort of a toy that we have, where we have 5 steel balls which are hanging from a support, and they are all touching each other. Now when we have steel balls, then when a steel ball hits another one, the collision is almost elastic, which means that even though there is a loss of kinetic energy, that loss is very little, and most of the kinetic energy is conserved. So even though it is still inelastic, but it's almost elastic. If we pull this one up to here and then we let it go, it will move downwards and hit this ball, and as it does that, the last one moves off and comes up to almost the same height, and then this one goes back and hits it, and this one moves off. So this keeps going for a while, and then it ultimately stops because it is not purely elastic. If it were, it would continue forever. Now if we apply the momentum conservation equations for this condition, and we assume that the mass of each ball is m, and we can call it m1, m2, m3, and so on, and it hits it here with the velocity u, then what is the speed with which this one leaves off? So we apply the sum of the momenta in the x direction initial is the sum of the momenta in the x direction final. There's no motion, well, here there's motion in the y direction, it's coming down, but in this part it's horizontal. So this is going to be m, let's call it m1 for ball number 1, and u1, that's the speed with which it hits it, and this, let's call it 1, 2, 3, 4, 5. So it's m5 times the v of 5, and because the masses are all equal, therefore this ball leaves off with the speed that's the same as the speed of u that we get from the momentum conservation. Now let's consider a case where we have 1, 2, well, they should be touching each other, 3, 4, and the 5th ball is here. So it's the same situation as here, and well, the first ball is here. As it falls down, goes and hits it, we've glued these two together. So 4 and 5 have to move together. So they will swing off like this. Both of them together will swing. And now let's apply momentum conservation equation and see what it will come up to here. That's where it will come and hit it, and they will swing off. So we can apply the sum of the momentum x initial is the sum of the momentum final in the x direction. So this is m1 u1, that's the speed with which it hits here, and this will be m4 plus m5, and they go off with some speed v. Let's call it v5. Well, because the masses are all equal, so this will be mu1 and this will be 2mv, so the m will cancel, and the v5 is going to be half of u1. So together they will go off with half the speed of what's hitting it. This is from momentum conservation. Now let's see what happens to the conservation of kinetic energy, because it should almost be conserved. So we see what is the sum of the kinetic energies initial, and it should be equal to the sum of the kinetic energies final. So the initial kinetic energy is half m1 u1 square, and the final kinetic energy should be almost equal to that, half. The mass is twice of that, so it's 2m1, as we did here, and the speed we found to be half of u1. Now when we can cancel this out, this will be 1 by 4, so it's going to be equal to 1 by 2 half m1 u1 squared. So we see that that was the original kinetic energy, and this is the final, which is K final is half of K initial. So it's far from being an elastic collision. However, we know it's an elastic collision, and therefore this is in doubt. So let's use the conservation of kinetic energy equation that we did last time, and we had V1 was m1 minus m2 over m1 plus m2 times u1 plus 2m2 over m1 plus m2 of v2. Sorry, this is u2. We did this kind of equations earlier, and this would be 2m1 over m1 plus m2 u1 plus m2 minus m1 over m1 plus m2 u2. So u2 is the initial velocity here, which is 0. So u2s are 0, and the masses are all equal. So v1 is going to be m1 minus m1, sorry, m2 is going to be now 4 and 5. So m2 is going to be 2 of m1 because there are 2 of them here. And so this will be 1 minus 2, so it's minus 1 over 1 plus 2, so it's going to be 3 u1, and from this equation v2 is going to be 2 times m1, that's 2, and 2 plus 1 plus 2 is 3 u1. So we get v1 is minus 1/3 u1 and v2 is 2/3 v1. So what we would expect is that these are the number 1 is going to come in from here, that's 2 and 3, and 4 and 5 would have been here. So this when it hits it, well, that should be here. Okay, it comes and hits it and comes here. So this is 1, 2, 3, 4, 5. So 4 and 5 go off with the speed that's 2/3 of u1, and this rebounds and goes backwards at 1/3 of u1. And this is what the kinetic energy equation gives us. Let's see what happens to the momentum. So we see px initial equals sum of px final. So it's going to be, the initial is going to be m1 u1 plus 0, and that's going to be, the final is m1 minus 1/3 u1, and m2, which is 2m1 2/3 of u1. So this is going to be, we just take out the m1 outside, it's going to be minus 1/3, and that's 4/3 of u1, which is 3 by 3 u1, which is m1 u1. So m1 u1 equals, the initial equals final. So the momentum is also conserved.